In this video, I want to talk to you about thin film interference. I'm just turning the light on, I forgot. There we go. So I'm going to first talk about the problem-solving strategy, which is this, and then I want to do a worked example on the next board. So let's get into it. So when you have thin film interference, even though it seems obvious maybe and goes without saying, you should first identify what the thin film is. I mention this because in a lot of problems in textbooks, you'll see a picture that maybe looks like this, where you have some materials and the picture is never drawn to scale, right? So in this case, for example, we see that the piece of glass is almost the same thickness as the oil. Now, you usually have to read, and maybe they'll say a thin film of oil is present on a slab of glass or something. So read the problem carefully and look for words which indicates what the thin film is. And I'll give you an example, like I said, in a minute. So in this case, I want to assume that we have a thin film of oil. You have a little droplet of oil that spreads out and maybe makes this weird parabolic looking shape on a slab of glass. So the slab of glass in practice is probably much, much thicker than you would show on this board. So the glass is huge, very thick. The oil film is super thin, and then we have air up above it. All right. Number 2, determine the number of phase shifts associated with reflections. So we've seen that when you have a wave traveling and it hits for example, let's talk about a wave on a string. If you had a wave on a light string that then hits a heavy string, we saw there was an inversion of the pulse upon reflection. Similarly, if you have a light wave coming in and you hit a higher index medium, a medium with a higher index of refraction, there's a phase reversal upon reflection. So basically, if you have light coming in and it hits this oil, going from air to oil, you go to a higher index of refraction. Ray 1, when you reflect it, would have a phase shift. It would invert. So there would be a phase shift associated with ray 2. And then, with ray 1. And then also with ray 2, we're going from 1.3 to 1.5, that's a higher index. This one would experience a phase shift upon reflection. So an extra half wavelength for each of those two rays. Now ray 3 has nothing to do with the thin film. I drew it just for practice, but notice in this case, we're going from 1.5 to 1. That's going to a lower index. No lambda over 2. So I'll say lambda over 2, lambda over 2, no lambda over 2. What do I mean by that? In this case, we have lambda over 2 shift for both rays associated with the thin film. And maybe so let me do something here. Rays 1 and 2 are the two reflections that we care about for our thin film. We have 2 lambda over 2 shifts. Okay, so in this case, all we care about are rays 1 and 2. I could now erase this one because it has nothing to do with the thin film. We don't want that to distract us. All right, identify our constructive and destructive equations. That's these two conditions down here. Look, this one has basically an odd number of half wavelengths. This is a way you could write an odd number of half wavelengths. If you don't believe me, look, plug in 0, we get 1/2 lambda. Plug in 1, you'd get 3 half lambdas. Plug in 2, 5 half lambdas. So this is odd number of lambda over 2's. Now, is this going to be constructive or destructive? Your gut instinct is to say, oh, lambda over 2, destructive, right? That's like saying something's hitting a crest when something's hitting a trough. But that's not enough for thin film interference. We need to also consider if these lambda over 2s are going to affect it. Now, if you have an even number of lambda over 2 shifts here, that's equivalent to a full wavelength shift. You're still cresting at the same time. So if you have an even number of lambda over 2s, we would say condition 1 is destructive and condition 2 is constructive. Again, look, this is basically an odd number of half wavelengths. This is essentially an even number of half wavelengths. 1 lambda is 2 lambda over 2. 2 lambda is 4 lambda over 2. So essentially, if you have an even number of phase shifts, conditions 1 and 2 are just like you expect. The one with the half lambda gives you destructive. The one with the not half lambda gives you constructive. However, you could imagine a different situation. What if this was air, oil, air? And if that was the case, maybe you'd have ray 1 gets a lambda over 2, but ray 2 would not. In that case, you'd have only 1 lambda over 2 shift associated with reflection, and then the conditions would flip. So that's what you're constantly worrying about. You can't just blindly grab the equations. You have to think a little bit before you use condition 1 or 2. So sometimes condition 2 is destructive. If you have an odd number, well, let's just write this. Even, constructive. I'll say even number lambda over 2s, constructive. Odd lambda over 2s, destructive. Similarly, over here, even number lambda over 2s, destructive. Odd, constructive. Okay, so the combination of this and this is what gives you constructive or destructive. In case you're wondering, where does this index of the film, why does that show up? What happens here is when light enters the medium, the wavelength changes. I think this is discussed in one of our earlier videos, but essentially in the thin film, lambda in the film is equal to lambda in the vacuum over n of the film. And so what we're trying to do is think about, okay, how much extra path length is traveled? So, right, because the light ray that goes, okay, obviously light ray 1 reflects. There's some glare off the front surface. There's a light ray that travels farther here, and so that thickness will basically determine how far you are along in the wave, whether you're at a crest or a trough. And so that's really the origin here. And the N film actually comes from the denominator over here, but we usually write it like this. So essentially, the index of refraction, you could think of it as modifying the wavelength or modifying the thickness of the film, but you don't want to do both. All right, so let's see, what else? If necessary, determine an equation for the thickness. So usually when you see a situation like this, you would draw some coordinate axis. And you could say something like y is equal to, maybe in this case it's negative 2x squared plus 4 or something, and there would be units on these, or sometimes you'd have to derive this algebraically. We'll do an example in just a minute, but notice the thickness in this case would be y. So in order to determine an equation for the thickness, what do you usually have to do? Draw a coordinate system and then describe some height or thickness of the film or width of the film in terms of some parameters. Okay. Finally, you reread the question and solve. Okay. And now, a couple of other notes before we do the problem, just so you have the terms right. When the thickness varies, we see a pattern, and I think you saw this in the soap bubble. Sometimes you see a bright and then a dark and then a bright and then a dark. We call those bright and dark bands fringes, right? So obviously if you have a uniform thickness, it's either going to be bright, dark, or some fraction thereof. And then, but when the thickness varies, you'll see bright and dark fringes. Another little comment here. We often show the incident light at an angle like this because it just makes it easier to number and label these reflections. But when we are doing thin film problems, unless you're specifically told otherwise, assume the light is at normal incidence. I'm going to say that again. Unless you're specifically told otherwise, most thin film problems assume light is at normal incidence. It's just if it's coming straight down, right, all the light rays are coming back up, it's hard to label them. So a lot of times, it's easier to label them here, assume normal incidence. Okay, so assume the light is coming straight at the film. You ready to do a problem? Let's do it. Let's go over here to this board. All right, this is, I'm on page 38 and 37. Maybe let me say one last thing. If you want to read more on this, I apologize, page 37. Why don't you skim through that? If you need to, pause the video if you want to read and see if there's anything else I missed. And now I'm going to go to this problem, which is on page 38 of volume 5. Okay. All right. And then we're going to assume that the wavelength is given. All right. And we're going to assume we have two slabs of glass. As a visual, I have those here. It's funny, I can actually see the pattern when I'm in the classroom, but there's no way I'm going to show you this on Zoom. It's just, I tried, it's very difficult to get this one to show up. But so I have two slabs of glass like this. There you go, you can kind of, all right, we have two slabs of glass. Let me just make sure, right? So two slabs of glass, and they're basically flat. And then I know this looks like there's a huge angle here, but it's just like this where it's a negligible difference here. So these two slabs of glass are essentially flat, but imagine there's maybe a dust particle or something at this end, so that if we could exaggerate it, right, there's a tiny particle under here that's causing the gap, all right? And in practice, the gap is so small, this angle is very close to zero. We have to be able to label something, so this is what it looks like. There's an incident ray coming in, and then there's air, then one glass plate. This particle causes a tiny air gap between the glass plates, then there's glass, and then down here we'll assume there's air again. All right? The slabs, the glass slabs, each have length L. Okay, so the piece of glass has distance L. Distance L. The little particle that's in here, we're going to assume has some diameter D. In theory, you could use the interference pattern to work this problem another way and figure out the size of the particle. People do this in labs and actually can then improve the flatness of the glass plates. All right, more on that if you care, read about interferograms. Okay, angle is insanely exaggerated like we saw. We know the wavelength. Do we know the index of refraction? I'm going to assume, well, I guess we don't, yeah. We're told this is n equals 150 if you care. 1.50. All right, air, index of refraction is 1. We're going to assume that, what is it, 1.00079 or something usually. It depends on humidity and all those. Okay, whatever. Let's start at A. Which reflections produce the thin film interference? Pause the video if you want to try it yourself. 3, 2, 1. It's going to be these two. 3 and 4 are the only ones we care about, right? The thin film is the tiny pocket of air between the two glass plates. So as a result, I don't care about 1 and I don't care about 4. These are the only two. So remember, it is the interaction between the reflection off the back surface of the top slab of glass and the front surface of the lower slab of glass. That's what's going to cause the little pattern that we see. Most of the light goes right through. When you look at this, most of the light goes right through glass. We're talking literally about the interference of glare from this surface and with this surface. So we're looking at the top two surfaces of this, we're looking at the bottom surface of this piece of glass. There's light reflected off that surface, and there's light reflected off this, and there's a tiny air gap. Okay, enough said. So 2 and 3. Are there 0, 1, or 2 phase reversals, or lambda over 2 shifts? Pause the video if you want to try it yourself. 3, 2, 1. Let's see. 2 is going to experience no lambda over 2, right? Because we're going from n 1.5 into n equals 1. When you go from high to low, no phase reversal. So I'll call that ray 2. No lambda over 2. Ray 3. One lambda over 2. I'll just say has lambda over 2. Shit. So we see it has 1 phase reversal. Now, is 2n film t equals n plus a half going to be constructive or destructive for this problem? This is going to be destructive. We have an odd number of lambda over 2 shifts, an odd number of phase reversals. That means the constructive equation gets the n plus a half. Remember, this is something like odd number times lambda over 2. We have an odd number of lambda over 2s that's constructive because we get an extra lambda over 2 from this one reversing and this one not. Next, at the left end, where the thickness is 0, right here, okay, very close to this, right, very close to the left end, there is still a tiny air gap right here, right? Are we going to expect a bright or a dark fringe? 3, 2, 1, here we go. I would expect this point at 0 thickness to give me a dark fringe, right? Okay, so how do I know this? I see that 2n film times thickness equals m lambda will be destructive. How do I know that? The m plus a half is constructive, so the 2nt film lambda vac is destructive. What are the values? M equals 0, 1, 2, etc. Notice, if thickness equals 0, that corresponds to m equals 0 in this equation. If thickness equals 0, this equation can never work, because even if you set m equals 0, this side would not be 0. So the trick is, when you see some question is, at the spot where the thickness is 0, will you expect a bright or a dark fringe? You basically use this requirement and say, which of these equations is valid for what? And so in this case, the 0 thickness case corresponds to destructive. I would expect it to be dark. I don't know if that made sense to you. I'll try one last time. Again, you do these steps, you identify which one gets the m plus a half and which one gets the not plus a half. The not plus a half corresponds to 0 thickness. okay? Because you can use m equals 0 and get 0 thickness there. So that tells you, and if this case, the destructive condition applied to the m lambda, so that means it was dark. Okay, let's try to find an expression for the position of dark fringes. And by that, I mean horizontal position based on this coordinate system here. What was the step that we need to do? Do you remember? You can pause the video and think what you need to do. I'm going to proceed in 3, 2, 1. We have to get this equation for the thickness. So we're going to use the picture to get an equation for the thickness, then we'll reread and solve. All right, so in this case, I don't know, let's see, the height of this air gap is what we're looking for. Is this quadratic? Is it exponential? Is it a sine wave? This is linear. So what I'm going to do in this coordinate system, it looks like we're calling y up and down, x this way. It looks like I could write y equals slope x plus intercept. And a lot of you might be saying, why don't you just write y equals mx plus b, dude? You're right, I could do that. But in physics class, I usually just write it like this because half the time m is mass. In these problems, m is an integer. I don't like reusing the same symbol. So that's why for this, I like to just write out the words and then think about it. Okay, so if you want to pause the video and see if you can crank out the rest, parts E and F, go for it. I'm going to proceed in 3, 2, 1. Here we go. The slope, that's rise over run in this case. Rise is D, run is L, so this should be D over L, X, plus intercept. In this particular problem, the intercept is 0. Just think, I could mix this test question up and have the particle at this end, just so you have a different equation, right? It's easy to mix things up that way. Plus the intercept is 0. Now, in this particular problem, what we've just described is an equation for this line and this height, y. Isn't that also the thickness? So in this particular problem, y is equal to the thickness. Sometimes what happens in other problems is you actually have some other distance and subtract off y to get the thickness or something like that. So be careful. Just because you can write an equation for a surface doesn't mean that's the thickness. In this particular problem it is. Sometimes you have to do a subtraction or something. Okay, so for us, we now are looking for an expression for the position of dark fringes. Well, let's use our destructive condition and we'll plug in the thickness of the film. So now 2n film times the thickness, which is d over l x, in this case, equals m lambda. What are we trying to solve for? Position. What variable is that? In this case, it's probably implying horizontal position. So what is x equal to? X is equal to, and maybe what I'll do is say this is x dark, just to keep track because we came from a destructive. I'll say x dark is equal to, let's see, I'll get an m lambda L over 2 n film D. I'm going to double check and make sure I didn't screw something up. L comes up, m lambda L, 2nd on the bottom, looks good. So this is the result for part E. And strictly speaking, we should specify what the heck m is. Because a lot of these physics equations, sometimes they'll start at m equals 0, sometimes they'll start at 1 and only specify the odds. So strictly speaking, come on, we should tell people what values of m are appropriate in this equation. So you should do that. If I ask you to write an answer and you leave this off, I'll probably ding you something, all right? You gotta tell people what values of m to use. Different textbooks will write these equations different ways. Some places will say m minus a half lambda and start at 1. So that's why, that's one reason I can think of that you better do this. All right. Part F, distance between adjacent dark fringes. If you want to try that yourself, go for it. Okay, here's what I'm going to do. I'm just going to use x dark 1 minus x dark 0. So in this case, right, you could just, now because this thickness is changing linearly, it's going to be the same. For, right, the distance between two dark fringes here is going to be the same as these two, the same as these two, the same as these two, because the thickness changes linearly. So in this case, we could just go plug in m equals 0, that's 0, plug in m equals 1, and what do we get? We see that the distance between adjacent dark fringes is this. This is the answer to part F. So I just took the position for one of them and subtracted a nearby one and adjacent one, and I got the result. Let's check. Meters times meters over meters, that gives me meters. N is a dimensionless quantity. This would be units of meters, that's a distance. So this looks good. Now here I have a couple of what ifs. Give me just a second. I can't see, my monitor turned off. Come on, computer. There we go. I have two what ifs. I want you to think about what would happen to the fringe spacing if you had a larger particle. If you want to pause the video, go ahead. 3, 2, 1. Fringe spacing is this thing. It's the distance between adjacent fringes, right? So that's what I mean by fringe spacing. If that wasn't clear, sorry about that. So if you use a larger particle, what happens? If you use a larger particle, you get a larger denominator, the fringe spacing goes down. Well, let's think about that. If, sorry, it's not quite on the, let me go back here. Let me zoom out just a little bit. Oops. Ah! Sorry. Oh my gosh. Sorry, I'm making this take longer than it needs to. I meant to do zoom out slightly. There we go. So in this case, think about it. If you used a larger particle, right, the ramp would be going up more rapidly. The thickness would change more rapidly. You're going to more rapidly change from dark to bright to dark to bright. The fringe spacing, it makes sense that it gets smaller if D gets bigger. What about the wavelength of light used? If you use a higher frequency of light, how would that affect the fringe spacing? Higher frequency of light, let's think. C equals F lambda, so lambda is equal to, and this is vacuum, we usually don't label that there. C is just the special one in a vacuum. So if you use a higher frequency, what happens to the wavelength? If frequency goes up, wavelength goes down. Blue light has a very short wavelength. Red light has a very long wavelength. The long wavelength can get through at sunset. The blue gets scattered everywhere, okay? So if you go to a higher frequency, shorter wavelength, closer fringe spacing. All right. Let's call that good. We can do another problem.